times 7.
Yeah, you're just going to have to wait. I mean, we're not doing a quiz or anything. Just hang tight. All right, good? You're good with that?
Yeah.
Good. Well, I mean, no, because it's going to take everyone. No, leave it up there. But I want to see your, where's your little, okay, you have yours? Let me see yours. Thank you. Is that a holder? Does it work? Oh, it doesn't work. Okay. All right, so this was the 1-inch group, right? Okay. You have yours, half-inch. Can I see it?
Yes.
And you know the volume?
Yes.
Yes? Okay. And then my 2-inch group. Y'all have it constructed yet? How about over here? Still working. We have some perfectionists over here. That's good. Perfect. Your screen is like destroyed. Okay, this was the 3-inch group, half-inch group, 1-inch group. We're waiting on our 2-inch group here. Okay, that's fine. All right, come on. Better be straight. I want to be able to pour water into this later. I'll find a way.
Actually, there's paper cups.
Yeah. I only need it for a little bit.
Probably be good for about 30 seconds.
Do you know what I'm going to ask you after I have these 4 up here?
What's got the greatest volume?
Yes. I am going to ask you that if we ever get the 2-inch one up here.
Have y'all ever worked for the government before?
Right. Oh, lunch break.
Or a union?
Yeah, but theoretically, do we lose all? What do we lose? What do we lose?
All right, your company's out of business because you couldn't produce the material. You couldn't produce the containers fast enough.
Yeah. That's okay. It's government funded.
Quality over quantity.
Quality? Yeah, I understand.
63.
I understand. People will pay for quality.
What would it be?
Oh.
It doesn't have to be perfect.
Oh. Okay, that's fine. Thank you. Okay. All right, so the first I think logical question is, does it even matter? Are these all going to have the same volume?
We thought about it.
We thought about
What do y'all think? No? My other class, everyone was like, no, they won't have the same volume. And I was surprised because most of the time people will say, no, it shouldn't matter. They're all going to have the same volume. So here they are,
I think it's okay.
half-inch, 1-inch, 2-inch, 3-inch. So what you give up, right? The bigger the square, the deeper the box is, but you lose the width and the length. Here we have a very wide and long box, but it's not very tall. So what was the volume you had?
37.5 cubic inches.
37.5
Yeah.
cubic inches. 1 inch? What is it? 58.5. 2 inch? 63. 3 inch? 37.5. So somewhere in here is the best solution, right? These two are not them. But what, does it have to be half inch, 1 inch, 2 inch, 3 inch? Could it be, I don't know, 3.672 inches? Yeah. Sure, right? There's nothing that says it has to be a nice number. So the most natural question would be, how do I create the box to get the most volume, right, out of it? Right? Does that seem logical to you? We want to be able to carry the most stuff inside of it. All right, so let's look at the setup of it. Y'all can break up if you don't want to sit like that. Y'all can spread back out. So you shouldn't have 5 at one table. We're going back to the lecture now. Okay, so look. Let's look at this from a calculus point of view. Here's my 8.5 by 11 sheet of paper. Right? And I'm going to cut out a square, but instead of using half or 1 or 2 or 3, let's let that be a variable. So let's let that be just some arbitrary value. Let's call it, how about just x? Because if I decide I'm going to measure out x, then this would also be x, right? So this little square would be x by x. And then this right here would be the same thing, and then this would be the same thing, and this would be the same thing, right? So those are all x by x. Then I go and I fold up the edges. And when I fold up the edges, I get this 3-dimensional container that looks like this, right? Ooh, bad. That was real bad. Oh, that's bad too. That was actually pretty good, now that I look at it. Good enough. Okay, there's my container, right? So the volume of this, I think you all were able to determine length times width times height, right? So let's look at this edge right here, which would actually correspond to this length right here, wouldn't it? How long is that? 8.5 minus 2 x's, because you have to take off the x's on each end, right? So this is 8.5 minus 2x. Okay, how long is this? Yeah, that's this right here. 11 minus 2x. Y'all okay with that? And then how tall is it? X. Right, because when you fold up those edges, this height is actually corresponds to the distance from, the x, right? Y'all got that? Sure? Okay, so this is x from here to here. So if I look at the volume of this, it's length times width times height. I could write it as, let's say, 11 minus 2x times 8.5 minus 2x times the height, which would be x. Agreed? And now my volume can be determined. If someone gives me x, I can give you the volume, right? So the volume is a function of x. I can write the volume as being a function of x. And what type of function is this? When you look at that, what do you think? Quadratic would be that, right? But it's a polynomial, isn't it? And since it's a polynomial, that's a good thing. We've worked with polynomials, haven't we? So I could distribute this out. Let's go ahead and do that. Let's distribute. Let's go 11 times 8.5. I think you get 93. Someone check.
93.5.
What is it?
93.5.
93.5. And then you do 11 times negative 2x, negative 22x. And then negative 2x times 8.5, which is negative 17x. And then negative 2x times negative 2x, which is positive 4x squared, right? And then you still have all of that times the x back here. Agreed? And distribute the x, collect like terms, and we should have a final volume function.
Let's find the most out of your volume function.
Well, no, this is just the volume function. That's all this is. This will give me the volume if you give me the x. So what will it be? 93.5 x minus 39x squared, right? Because I can put these two together and then bring an x into them, plus 4x cubed. All right? That is a continuous function, isn't it? I would love to know the global maximum of that. But I need a closed interval if I'm going to use the closed interval method, right? So think about x. X is the actual cut you're going to make. Is there a smallest cut that you could possibly do?
0.
0, which means you wouldn't cut anything, right? That'd be like somebody gives you this and says, make a container out of it by cutting the corners out, and you say, okay, I'm going to make a cut. It's 0 by 0. And then they fire you, right? And they bring someone else in. But that would be the smallest cut, right? So I could say, all right, let's take a look at this from 0 to, okay, now I have to be able to have a closed interval. So I need a biggest x that I could have.
So you can't go past 8.5.
3 was the biggest I gave y'all, but is that the biggest you could use?
No, you can't go farther than 8.5.
Can't go further than 8.5, which would be the width of the paper. I don't even know if you could go that far.
Maybe like 4.25.
I still need a square.
Go halfway.
Halfway.
So the square.
So what would halfway, oops, halfway across the page, the shortest side of the page? 4.25. Agree? If I do a 4.25 by 4.25 and then try and fold it up, I wouldn't even have any width to it, right? It'd be 0 width. So again, I get fired for that. But that would be the biggest I could go. Make sense? So 4.25. And so now, this is why we take calculus. We have a continuous function on a closed interval. We can find the global max, right? We can find out what it is, and we can find out where it occurs. The x, we can determine the x value that's going to give you the biggest v, right? The biggest volume. So let's do it. How do you do it? This is what your homework was about. You just, no, not trial and error. Find the derivative. You won't be able to get the correct answer if you plug in. You won't be able to find it. Huh? Find the critical points. Okay, so I need the derivative, right? Derivative of this is 93.5 minus 78x plus 12x squared. That's my derivative. Once I have the derivative, to find the critical numbers, I set it equal to 0. And I also figure out if it never exists. And what about this one? I'll look at this one because it's easier. It's polynomial. It's going to exist everywhere. That's not even worth me looking at, right? But setting it equal to 0, can I set that equal to 0? Sure. Why? Because it's a quadratic. All quadratic equations we can find solutions for using the quadratic formula, right? So we're in business. I don't think it's going to factor. In fact, I know it's not going to factor. So we have to use a quadratic formula. And if we're going to use the formula, maybe we should write it in the standard way, which is what we call descending order. Highest power of x down. And let's solve that. So you would use a quadratic formula, which says that the solutions to this quadratic equation, x equals negative b plus or minus the square root of b squared minus 4ac, all over that, right? All that stuff. So what's negative b? Positive 78 plus or minus, calculator please. B squared. Sorry, I don't know what 78 squared is. 6084 minus 4 times 12 times 93.5. All of this over 2 times 12. So 4 times 12 times 93.5. This right here is 4488. Okay? So I have equals 78 plus or minus square root of, okay, 1596 all over 24. And then at this point, we can leave it in exact form, or we can get the decimal. I'm going to get the decimal. So what is square root of 1596? 39.9, and depending on how precise we want to be, we could round it at, I like 39.95. Let's go with that. So this is approximately 78 plus or minus 39.95 over 24. We're going to get two answers, aren't we? Okay, see what happens. When I add 39.95 and then divide by 24, I get one answer of 4.91. I'm going to go 3 decimals, 4. That's close enough. I'm getting that as one answer. And then when I subtract, did anyone else get that answer? Anyone else get 4.91? Yes? When I subtract, I get 1.585, something like that. Anyone else get that one? Yeah? Okay, so we look at these critical numbers and we chunk one of them, right? We're throwing out the 4.914. Why? Because it's outside of our interval. All right, once I have this, what do? Plug that into the original function and plug in the 0 and 4.25. Although I should already know that plugging in 0 and 4.25 should give me no volume. Right? It should give me 0 volume, but I'll double check it. So what is V of 0? I'll do the endpoints first. V of 4.25, and then I'll do the V of 1.585. So is V of 0 easy? Yeah, that's just 0. All right, V of 4.25, check this out. If I were going to do V of 4.25, I would go back to the volume when we wrote it this way. Do you remember before we distributed? That was the volume before we distributed, right? If you plug 4.25 into this, do you see what happens right here? 2 times 4.25 is 8.5. And 8.5 minus 8.5 would be 0. So that'll zero that out. Do y'all see that? But you could do it also by just plugging it in. Plug it in right there. So you get 0 volume there, which is probably pretty indicative that that's going to be the max, right? The next one. So let's get on our calculators and let's do that. Has anyone done it yet? Plugging in 1.585 here, square it, here, there, cube it. No? All right, 93 point. What do you get? I'm not getting that. I'm getting 66.141. I'm getting about 66.15. That's good enough. All right. That's it right there. So if we were this company and we were manufacturing these containers and we wanted to get the most bang for our buck, right? Because we got to buy this precious metal. We want to get the most volume out of it, right? Then it's not going to be, we just check a few numbers, half, 1, 2, and 3, and then take the best. Because we would have gone with what, 2? Yeah. We would have gone with 2, because 2, they had a volume of 63. So we would have gone with this if we weren't calculus people. But because we're calculus people, what we realized is that we need to cut out exactly 1.585 or approximately 1.585 from each corner. If we do that, we're actually going to optimize it. We're going to get the most volume. We're going to get 66.15 out of this sheet. That's the best way to do it. There's no better way. These problems are called optimization problems, and this is coming up later. This is coming up in 4.5. We're going to do more problems like this. This is how you would handle an optimization problem if your function was on a closed interval, which it was here, which is why I showed it to you. We also need to be able to handle functions that are not on closed intervals so that we can, if we had to take this restriction out, can we still find these max and mins without that restriction? And that's what the next 2 sections are about. Is let's open this up, let's take it out of the closed interval, and let's see how we handle it. All right? We good? All right, that was just an exercise. I hope that it reminded you of what we've done and kind of opened your eyes to the way we do math in the real world. It's actually pretty interesting. We'll look at a question later. Did I talk to you all about the can already? No? You have a can right there. Okay, see, you want to hold up your can? Everyone's seen an aluminum can before, right? So that can, you can put it down. That can, you don't know, hold it up till 140. Can you hold, or till 240, yeah, to the end of class? Don't switch hands, just keep it there the whole time. No. All right, so look, when you build a can, right, if you're the company Monster, right, if you're the Monster company, are they owned by someone? Is it Pepsi? Whatever, it's not important. It's not.
No. Pepsi owns the other one.
Whoever owns that company, right, they have to buy the aluminum, or whoever makes their cans has to buy the aluminum, and they buy it in bulk, and then they create the cans, right? Yes? How many different ways can you create a can that holds, how many ounces is that? 16 ounces. Fluid ounces. So you could create a 16-ounce can that would look like this. Couldn't you? I mean, you could create a can. It's like this little thing, like, you know, a bunch of these markers stacked up, you know, and then you see someone drinking out of their can, right? That you could do it, right? You could do it. You could create a can that's somewhere in between, like this, 16 ounces. You could do this. You could do a can that looks like this big wafer, almost, right? You know, so people are like, you know, holding this thing, drinking out of it, right? There's all these different combinations. And just like with this, each one of those uses a different amount of aluminum. Each one of these has a different surface area, doesn't it? And the surface area is the amount of aluminum you need. So the company will look at it and they'll say, can I find an optimum way to create the can so that I can hold the 16 ounces but use the least amount of material? That's finding a minimum as opposed to a maximum, right? You want to use the least amount of aluminum. That lowers your costs. It turns out that if you do this correctly, and this is pretty amazing, just for an arbitrary can, the perfect dimensions for a can, the optimized dimensions, are that whatever the diameter is, that it's equal to the height. Diameter equals height. If your diameter equals your height, you have made the most efficient can possible. You have used the least amount of material. All right? That's the model. If we have time, I'll actually show it to you, how we can determine that. Now, does it look like that's what they did there? Why not? Why do you think do you think they don't care about costs?
They care about fitting it in your hands.
16 ounces. They care about getting them.
Yeah, there's a lot of factors. Is that a perfect cylinder?
No.
It's not a perfect cylinder. These cans, right? Can you hold it up again? Your can on the bottom, what's on the bottom of it, right? It's got this indentation. What's that indentation for? Because if you leave it in your car, if you put it in the freezer, right, it's going to, if you leave it in your car, it's going to get pressure and it's going to expand, and what that does is it pops out, it reverses, that little dome pops out the other way, and it releases that so it doesn't blow up in your car. Same thing if you put it in the freezer, it'll expand, same thing, so you don't lose everything. So they incorporate that, and then if you look at the top is not perfect, right, it kind of comes in a little bit, like this, and then they put a cap on the top of it, right? So it's not a perfect cylinder. If it were a perfect cylinder, this would be the best way to do it, but it's not a perfect cylinder. So, but they've incorporated that into their design too. They have a formula for that particular can. And maybe the thickness of the cap is different than the thickness of the walls. I mean, there's a lot of factors at play here. And then, of course, there's the whole PR thing. It's Monster. It's got to be a big can, right? Can't be a little can, right? Can't have a little Monster drink. So there's all these things that come into play, right? Yes? But if you're looking at it purely from the point of view of cheapest way to build, true cylinder, this is it. Then what we do in these companies is we just add the other variables in there. We get the model for that exact can. Does that make sense? and then you optimize it with calculus. But you have to be able to find the function. The function here would be, you would find the surface area function, and then you'd find its minimum. Understand? Okay. We are going to do more of that. But today is about the next section, 4.3. And where did the other one go? Half inch? Oh, this was the 2 inch. I'm going to give this back to you because you spent so much time on it. I'm going to give that back to you. It's a little memento for yourself there. Because I'm going to throw these away. All right. 4.3, derivatives and the shapes of graphs. Oh, we are skipping 4.2, everyone. We're going to come back to 4.2 later. I think I told you the mean value theorem was it stood on its own. You don't need it to do the rest. So we're going to skip it. So I have here a picture of a function. Everyone see that function? All right, I'm going to move across this function with a dot. Do you see my green dot moving there? And I want you to pay attention to the slope of the tangent line at that dot. The slope of the tangent line is this, well, this is the tangent line, right? The slope of it is positive. And that means that the derivative is positive, doesn't it? The derivative is the slope. So if I go to that point, whatever m is, it's a positive number. And as I move across this function, through the entire function, doesn't it remain positive the whole time? So what we're going to look at in this section is this idea of functions and where they're increasing and decreasing. This function we call an increasing function. Because if you read it like a book from left to right, imagine you're on a roller coaster, you're going up, aren't you? Increasing. So there's some connection between increasing and the derivative. If the derivative is positive, you must be going up. Yeah? As opposed to this function, which is the opposite, it's decreasing. And if I move along this function, notice that the slope of the tangent line is negative. So I'm going down as I move across from left to right. See the difference there? Excuse me, I'm still trying to get over my sickness here. What if a function is constant? Then the slope is 0 the whole time, isn't it? How about a mixture? Okay, so I'm going to start moving this point. Right now, the derivative is positive, right? Derivative is positive, so we're increasing. And when we get to the top, what's going to happen right at the top? Derivative is going to be 0, right there. So I've reached a local maximum, haven't I? And then as soon as I go to the other side of this, to the right side of that, what's going to happen? The derivative is going to be negative. So I'm going to start decreasing. Decrease, 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 till I get to the local minimum. And then right at the local minimum, it's what? 0. And then increase, 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 increase. So what's happening is we're looking at a way of maybe there's a method here where we can find these local maximums and minimums. Do you notice that they're occurring whenever your derivative changes from positive to negative? That's where you have a local max. Or wherever you change from negative derivative to positive derivative, that's where you'd have a local min. Yeah? Maybe. We'll see. This leads us to the first derivative test. And this is basically what I just said. Suppose that c is a critical number of a continuous function. What does that mean? What does c being a critical number mean? The derivative is either 0 there or does not exist. Okay? C is a critical number means that the derivative is either 0 or doesn't exist. Also, I should point out that this c is in the domain of the original function. Your original function must be defined here for you to call it a critical number. All right? If the derivative of the function changes from positive to negative at C, then f has a local maximum there. That's just the picture I showed you. If you're going to tell me that right here at C, you have a point, and you either have a zero slope or an undefined slope, and your derivative goes from positive, which means you're going up, to negative, which means you're going down, then at that point you got to be at a local max. On the other hand, if it changes, if your derivative changes from negative to positive, that would be the reverse of this. Here's a point, C. Your derivative changes from negative to positive, then that's going to have to mean you're at a local minimum. Does this make sense? Okay. If the derivative does not change at C, then you do not have a local max or a local min there. And I'll draw a picture of that. Although I think my animations will show it. Yeah, this picture will show it. Okay, there's my local maximum, right? I've color-coded the graph so you can see it. As I move, green means I'm going up, going up, going up, and then look, I start going down, that's my local max. So my derivative is positive here, is negative here. What's happening at this point? What's happening at this point, wherever it is, C? We have a local max, but the derivative up there is what? 0, right? So that's a critical number. We have a critical number here. The derivative goes from positive to negative, local max. The local min's here, right? So here's some point C, where my derivative is going to change from what? Negative to positive. So I'm going to have a local min here. What if you have a critical number where it doesn't change? Do y'all see a critical number in here that I didn't mark? At the origin. Everyone see this one right here? This is a critical number because the derivative here is what? 0, right? Slope tangent line 0. But what's the derivative doing there? To the left of it, what is it? Going down, so it's negative, 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 then it flattens out to 0, right? And then you go to the other side, what does it do? Still negative. See, it didn't switch. It went from negative to 0 to negative. There's no change in sign there. When that happens, this is not a local max or a local min. So you have to have the change for it to happen. With me? All right. I think I'm going to do this second part in a set in just a minute. Let me show you something. Let's take a look at this function here. This function gets people in trouble. Look at the function f of x equals 1 over x. All right, can you tell me the critical numbers? So take the derivative. What's the derivative of this function? Negative 1 over x squared. We've done that, I think, enough to know, yes? All right, tell me where's this derivative 0? Well, no, not at 0. A fraction can only be 0. A fraction can only be 0 if the top is 0. Can the top of that ever be 0? No, so actually we don't even have this, do we? How about where the derivative doesn't exist? At 0. Do you all agree with that? At x is 0. But, is that truly a critical number? Why not? That is a place where the derivative doesn't exist, right? But why is it not a critical number?
Because it's not a change.
Do you need to go walk around? Yeah, go walk around. Go get some Monster. Oh, you have a Monster. Shit, that stuff doesn't work. Here I am advertising for them.
Is it because there's no change?
What do you mean no change?
Positive, positive.
Yeah, when positive, positive.
Well, we haven't checked that. That's a good point. We haven't checked that, but
over 0?
Let me see. Let me bring this up. Go back up here to when we talked about critical numbers. Okay, read that again. A critical number of a function, f, is a number c in the what? In the domain of f. Okay. In the domain of f. Oops. Get back to where I was. I was right there, right? Okay. Is this a critical number? Why?
Because you can't have 0.
0 is not in the domain of f. Agreed? It's not in the domain of f. It does make my derivative undefined, but it's not in the domain of f to begin with, right? Now, let's just take a look here for a second. What would happen if I were to try and figure out what's happening to the left and to the right of that? So let's imagine here at 0 we have something interesting is happening at 0. Do we all agree with that? Let's just check. Let's pick a point here and pick a point here, like -1 and 1. We could do a limit, but let's look at the derivative, because this section is about the derivative and how it tells us if we're going up or down. At 0, something very bad is happening, right? Not only to the derivative, but to the original function. If I look to the left of 0, like to -1, can you tell me, I'm splitting up my number line to two parts here. Can you tell me what happens to the derivative over here? So what is f prime of -1 going to give me as an answer? Plug -1 in here. -1 squared is 1. -1 over 1 is -1. Do you agree? -1? That means that over here, the derivative is negative, less than 0, which means that the original function is doing what? Going up or down? Decreasing. I'm going to use an arrow to represent decreasing. Do you understand what I just put here? At -1, the derivative is going to be negative, which means that the original function is going down over there. How about over here? What's happening at 1? It'd still be going down, -1. Agreed? So the derivative over here is negative, which means the original function is going down. What I'm trying to illustrate here is that with a function like this, if you're not careful, you're going to think that you've got a derivative that doesn't exist, right, at 0, and that it goes down and continues to go down. So you might think that your picture maybe looks like this. Do you all agree that that would follow into this pattern? It's decreasing, and then what? Vertical tangent line here would be undefined, and then going down. But this, in fact, is not at all what it looks like. There's something wrong. If you actually graph 1 over x, it looks like this. Does that make sense? Let me throw a slightly different function up here and see if we can make the same sort of mistake. Let's do this one, 1 over x squared. Let's evaluate that one real quick. What's the derivative of that? -2 over x cubed. I'm just going to trust everyone can do that, right? Yeah. All right, so again, if we're not careful and we try and say, where's the derivative 0, you would say what? That doesn't happen, right? Then you'd say, where's the derivative not exist? And we're not being careful, so we say what? 0. So you're saying, okay, derivative doesn't exist at 0, so I have a critical number at 0. That's us not thinking. So I say, okay, at 0 I have something cool happening. Let me check over here and see what happens. Let me check over here and see what happens. So let's plug -1 into the derivative. Tell me what happens if you plug -1 into this derivative. You get +2. So my derivative over here would be positive, which means my original function is doing what? going up, right? If I plug 1 in, then what happens? I get -2, so my derivative is now negative, and that means my original function is going down. So you're sitting there going, oh great, guess what I just found? A local maximum. Because you say, oh, I have a critical number at 0, and it goes up and then down. There's a local maximum. And you're wrong, right? Because it's not defined at 0. So we're about to do problems where we're going to do this. We're going to find local maximums, but we have to pay attention to what that little first derivative test told us. If you have a critical number and it changes signs there, then yes, you will have a local max or a local min. But it must be a critical number, and to be a critical number, it has to be in the domain of the original function. With me? This was not in the domain of the original function. So we would not consider that a critical number. Yes?
Can you show us an example where it does not exist, does belong to the original?
Absolute value of x would be an example. That would be an example of one where you would go from what, decreasing to increasing, and it would be a local minimum, and the derivative doesn't exist there. Is that good? Is that what you wanted? Yeah. All right. So our first derivative test tells us where we're going up and down. So we're gonna do a problem now. Ready? Let's go with this one. F of x is x to the 4th minus 2x squared plus 3. What I'd like for you to do is this. Find where f is increasing and where f is decreasing. Does this notation make sense to you? Tell me where this function's going up. Tell me where this function's going down. Then, after you do that, find any local max or mins. I could have more than one. Maxes or mins. I think you get what I mean. Y'all understand? All right, so notice there's no closed interval here. We're not asking for absolute max and min on closed interval. We just want to know, hey, look at this function. Where does it go up? Where does it go down? Where does it go down and come back up? Who knows? So we're going to use this first derivative test. And here's the way we apply it. First, I'll take the derivative. So the derivative is pretty clean, right? 4x cubed minus 4x. Oh, that's real nice, right? Now I will find the critical numbers. Because if I'm going to have any ups and downs or ups and downs left or right, ups or downs, maxes and mins, it's going to be at the critical numbers. So we do what we did before. Figure out where this derivative is 0. That's pretty clean, right? How are you going to solve that? Factor out of 4x, be left with x squared minus 1. You can continue to factor that, x plus 1, x minus 1.
So you get -1 and 1 is your answer.
You get 3 answers, actually. 0, right? Set that to 0, that to 0, that to 0. 3 answers. 0, 1, -1. All of these are critical numbers. Why are these all critical numbers? They're all in the domain of the original function. The domain of the original function is all real numbers because it's polynomial. So we're good to go. These are 3 numbers, right? Can we shut that door by chance? Thank you. Those are all your critical numbers. Now, the way I'm going to show you that I do this is usually different than the way the book does it and the way most books do it. Most books do this thing called a sign table, and I just don't. All right? And it's only because when I was learning it, the sign table didn't make sense to me. And so I teach it the way it makes sense to me. So So if you go look in your book and you see these little pluses and minuses and stuff, I didn't show you that, okay? So here's the process that I follow, all right? What I'm going to do once I find my critical numbers is I'm going to plot them on a number line. 0, -1, and 1. I'm also going to put a little box around these guys because I want to make sure that I don't confuse these with anything else that I put on here. Those are critical numbers, right? If something is happening as far as like local maxes and mins, that's where it's going to happen. But these three numbers partition my number line into 4 sections. Do you see this? I create 1, 2, 3, 4 sections from this. What I'm curious to know is what's happening to the original function over here. Like, is it going up or is it going down? I don't know. In this region, what's it doing? So the way I could determine that is to pick, not plug this in, plug something over here in and see what it does. So let's pick a number over here. What do you want?
1.5.
A nice number. -2? You could do 1.5, but -2. And I circled it. And notice I put a little X here because this is my little test number. Circled it, not to confuse it with the box numbers. I'm going to test this number. I'm going to test it by plugging it into the derivative. Because the derivative tells me if I'm going up or down. Right? So underneath this, I'll just write it down. What is f prime of -2? So I go over here to my derivative, and I plug in -2, and I see what I get. What do you get? -2 cubed, -8 times 4. So -32, and then minus plus 8. Right, because it's -4 times -2, so plus 8. What is that? Negative. It's negative, right? Negative something. -24. Who cares? It's negative? That's all I care about, right? I only care that it's negative, because what does that tell me? Over here, my function is going down. Understand? So if you want to write -24 or whatever it is, fine. I'm just going to put negative and circle it, because that's what I care about. So up here, in this little region, I'm about to draw something. The derivative over here being negative means that the original function f is going down over here. Follow me? The original function f is going down because the derivative is negative. Negative slope means down. And then I need to do that for every one of those 4 regions. So what's the next next little test point I should pick? Kind of.
We were like in algebra when we were graphing polynomials and we are trying to figure out if they were tangent.
What we were doing in college algebra, if you did this with polynomials for, or you did it for rational functions for sure, when you did test points, we were just trying to figure out if the graph was above or below the x-axis. Here, this is different. What we're doing is we're using the derivative to tell us where the function goes up and down, which is really kind of cool. We're going to be able to figure out this is a polynomial, right? And in college algebra, we could graph this, but we could never tell how high it went and how low it went. We're actually about to be able to do that. All right, so let's plug in. -1/2 is probably the best thing. So if you want -0.5, -1/2, and I get to plug that into the derivative. Hey, check this out, everyone. This is your derivative right here. Here's your factored derivative, isn't it? All you care about is if it's positive or negative, right? Sometimes it's easier to plug your test point into this version. Let's try it. What's 4 times -1/2? Negative. Okay, so I would get a negative there, wouldn't I? That would be negative. What's -1/2 squared? Positive 1/4. What's 1/4 take away 1? Negative 3/4. So wouldn't I have a negative times a negative? Which would be positive. Look, this is calculus 1. I expected everyone could take -1/2 and plug it in there and get an answer. But to be quick, I'm just going to say that in here we got a positive, didn't we? Since we get a positive, that means that the original function in here is doing what? increasing, going up. And then what happens if we plug in positive 1/2, which would be my next most natural test point? 1/2 in here. And 1/2 here. Positive. 1/2 here, it's going to give me the same thing that I just had. That would be negative in there, right? So positive times negative, negative. So it goes down. And then one last test point. 1.67, I'm just kidding. 2? I'm kidding. 2? You could pick 10. It doesn't matter what you pick. All right, I like to pick nice numbers. But 2 in here, it's positive, right? That's going to be a positive number. 2 squared minus 1, that's positive. Positive times positive is positive. So it goes up. Are we good? Any questions?
Yeah. When it comes to concerning polynomials, is it pretty much a given that once you start the process of the local minimum maximum is changing direction, does it just keep doing that until it hits its continuous point?
I was hoping somebody would ask me that. No. The question is this. Is it with polynomials that when you do this, that you can just get the first one and just assume that they'll switch as you go? And the answer is no.
Isn't there a certain amount of numbers though?
Mm-hmm.
Like if it's x to the 4th and then divided x cubed or x cubed, you know it'll cross the axis point 3 times. So when couldn't you guess
What would cross the x-axis? What would cross the axis 3 times?
the 3 turning points? Yeah.
Well, if you have this, right? This means that you have up to 3 zeros. You could have repeated zeros, which wouldn't count, so there could be an issue there. So look, trust me, if there was like a nice clean way where I could say, look, if we see a polynomial, just get the first one, it'll switch from then on out, I would tell you. But unfortunately, it doesn't. So yeah, we have to test each one. Yeah. These problems are gonna be long. I did 4 homework problems before on video, before I came here. 4 problems, it took me 1 hour and 20 minutes to do the homework solution videos I do for this class. 4 problems took me 1 hour and 20 minutes.
What was the homework?
I think it's 10 problems. Okay, so these problems these problems in this section right here are pretty long. The ones in the next section are even longer. So just be ready for it. That's all. These problems are going to take us 20, 30 minutes. This one's not so bad because we're almost done. All right. All right. So any questions? Any other questions? We did all the testing. Is it obvious to us that we can tell where the function's going up and down? Okay, let's actually write that down. Let's answer the question, which was to determine where it's going up and down. So f is increasing, colon, now let's express where it's increasing in terms of its like domain. Like the values of x for which it's going up. So would you agree it's going up all in here? Everywhere in here my function's going up. How do I express that in interval notation? From -1 to 0. So I'm looking at the x values. From -1 to 0 is where it's going up. Also, where? 1 to infinity. Agreed? That's where it's going up. So I write it like this. -1 to 0. Then we use that union symbol. And then 1 to infinity. When it comes to increasing or decreasing, no matter what your function is, always use open intervals. Even if you actually had a closed interval up here, when you talk about increasing and decreasing, you can always write your answers as open intervals. And it's not incorrect.
Is that universal or just your class?
No, that's universal. Because to define increasing and decreasing, the true definition of it, you need 2 points. And the end point by itself then doesn't matter because you always need one other point. So, yeah. All right, good. How about where it's decreasing? So it's this region over here forever. So negative infinity to negative 1, right? And then union 0 to 1. There you go. That's where the function goes up. That's where the function goes down. Let's find the local maximums and minimums. So how about local maximums? I'm put L max. Is that all right? L max? Do we have any? What am I looking for on that little chart over there?
Up to down.
Anywhere I'm going up to down, right? Where am I going up to down? At 0. So remember I told you in the last couple of classes that the maximum, when you ask for the maximum, they're usually talking about the maximum value. But I wanted as a point, right? As a point. That's the way we need to list this, as a point. So I know that at 0, if my x value is 0, I should be at a local maximum. What's the y value going to be there? How are you getting that? Plugging 0 into the original function. So this is where things start to get confusing. Like the test points are getting plugged into the derivative, but when you go to actually find max and mins, those points are getting plugged into the original. So you just can't get things mixed up. You got to know what's going into what. So I'm plugging 0 into the original function, and it's spitting out 3, which means written as a point, it's the point 0, 3, right? We need to start a revolution somehow. And we need to get rid of this whole interval notation and points looking the same, right? Like the point 0, 3, what we mean is the x value is 0, the y value is 3, right? But when we write this, we don't mean x and y, we mean all the x values between negative 1 and 0. But they're the same notation almost, right? We need to get rid of that. It's too confusing. The only way we get around that is maybe writing something like this. Instead of this, the set of x such that something like x is greater than negative 1 and less than 0, and then like x is greater than 1. Like doing a different notation. Something like that, like set notation instead of interval notation. Or you could say, for this one, you could say x is an element of the interval negative 1, 0, union 1 to infinity. So there are ways around it, but it's just more notation. X belongs to this interval or this interval.
It makes sense in here, but try explaining that out.
Yeah. All right, we good? Is that the only local max we have? Yes. How about local min? We have to plug in negative 1, right? Because we go from down to up. Down to up. And so I plug negative 1 into the original function and get... Is it? I don't think so. It's 1 minus 2 plus 3, right? So you get 2? Get 2. So the point negative 1, 2. And then, is that the only local minimum? No. Yeah, we have another one, right? We have another down to up. So we have 2. And this one happens at 1. If we plug in 1, we get the same answer, right? 1, 2. Bam. We're done. Are there any questions about the process here, what we just did? Anybody want to comment on just how awesome this is? No? Dead silence. There's the graph. How did we do?